What if you could peer beneath the dusty surface of Mars, or maybe even an asteroid, without digging a single hole? Sounds like science fiction, doesn't it? But today, we're diving into how the messy leftovers from space rock impacts.
The ejecta blankets.
Right, those scattered fields of debris, how they're giving scientists a totally new way to essentially X-ray these other worlds.
That's exactly it. For a long time, when we looked at impact craters, we mostly focused on the crater itself, its size, its shape.
Yeah.
But what's really fascinating and what this new research highlights is how the material gets blasted out and spread around. That tells a powerful story about what's hidden underneath.
Okay, let's unpack this a little.
Yeah.
We've all seen pictures, right? Craters on the moon, on Mars.
Sure.
My thinking was always, okay, studying them tells you how big the asteroid was, maybe how hard it hit. You're saying there's more, like another layer of info.
Absolutely. The traditional way looked at the crater dimensions, the depth, the diameter, and those features can tell you about the strength of the material, how tough it is, and its porosity, how much empty space is in it.
Right, like dropping a rock into thick mud versus, I don't know, sand, you get a different kind of hole.
Exactly. A different splash, a different crater shape, depending on that consistency.
So the new insight isn't just about the dent itself, but about the spray pattern. How far that splash of debris, the ejecta blanket, actually spreads out.
Precisely. This new research really emphasizes that the extent of this ejected stuff, how far it travels from the crater, is another really crucial clue about the subsurface. So the key insight is that the size of that whole debris field basically acts like a natural probe. It tells us if the impact hits solid rock or maybe something softer like ice without us needing to, land a drill.
Okay, that's where it gets really interesting for me. How did scientists figure this out? Was it just staring really hard at pictures of Mars?
Well, looking at Mars images was definitely part of it for confirmation. But the initial breakthrough really came from some pretty sophisticated computer simulations.
Ah, simulation.
Yeah. Researchers, including Gareth Collins over at Imperial College London, they developed these detailed models to recreate the physics of these incredibly energetic impacts.
So they built a kind of virtual Mars on their computers and started smashing virtual asteroids into it. Is that roughly it?
Well, in a very controlled and scientific way, yes, that's pretty much it.
Okay.
And this let them precisely control the virtual ground, the subsurface. They could swap in different materials they think might be down there.
Like what kind of materials?
Oh, everything from solid bedrock, layers of sediment, even things like icy deposits, maybe stuff left over from ancient buried glaciers, that sort of thing.
And by doing that in the simulation, they could see exactly how each different underground layer changed how the debris flew out, how far it went.
Exactly. The simulations showed a really clear pattern. Different subsurface materials and even different layers of materials caused a really noticeable range in how far the ejecta spread.
Noticeable enough that you wouldn't need to be like standing there with a tape measure.
That's the key point. The models predicted these differences in the ejecta radius could be big enough to be measured by instruments we already have orbiting Mars.
Oh, wow.
Like the HiRISE camera on the Mars Reconnaissance Orbiter, that's an incredibly powerful camera.
So this means we could potentially map what's underground just using orbital photos.
Potentially, yes.
Yeah.
Analyzing high-resolution images. It's a potential game changer.
Okay, computer models are great, but, how do we know this actually works on real Mars? Reality can be messy.
Right, that's absolutely crucial, the validation step. So the research team looked very closely at two quite recent impact craters on Mars.
Recent? Why recent?
Because they were fresh, their ejecta blankets hadn't been eroded away or changed much by Martian weather over time. Makes the measurements more reliable.
Gotcha. And I'm guessing these weren't just random craters. They picked them for a reason.
Exactly right. One crater was in an area where other data, like radar, strongly suggested there was solid bedrock pretty close to the surface.
Okay, bedrock case.
And the other one was in a region where there's really compelling evidence for a lot of subsurface ice, buried ice.
Okay, ice case. So did the real world match the simulations? Did the icy spot crater look different from the bedrock one?
It did, and exactly as the simulations predicted. The crater that formed over the suspected icy ground had a significantly smaller ejecta blanket compared to the one on bedrock.
Smaller. Interesting.
Yes, and that real-world observation strongly backs up the idea that what's underneath directly affects how far the impact debris gets thrown.
So what does this unlock for understanding Mars? Why is this new way of seeing underground such a big deal?
Well, it gives us a potentially invaluable new tool for investigating the Martian subsurface remotely from orbit. Imagine being able to scan huge areas of the planet and maybe pinpoint spots with buried glaciers, which would be vital for future human explorers.
Water.
Exactly, water ice. Or maybe find ancient lakebeds that could hold clues about whether Mars was ever habitable. We could identify these hidden features without landing expensive rovers and drills everywhere.
That is huge, finding buried ice easily.
Yeah.
Yeah, that changes things. But you mentioned this isn't just for Mars. It could work elsewhere.
Absolutely. The basic physics of impacts, they should hold true on any solid body in the solar system. Asteroids, moons.
Okay.
Think about the European Space Agency's Hera mission, for example. It's heading to the asteroid Dimorphos right now.
Oh, yeah, the one NASA's DART mission smacked into, the Planetary Defense Test.
That's the one. So Alexandra Sokolowska, one of the lead researchers here,
Okay.
she pointed out that the ejecta from that DART impact, the stuff that didn't escape Dimorphos completely but sort of settled back down, that debris could hold really valuable clues about the asteroid's insides, its structure, what it's made of.
So analyzing how that debris fell back tells you about the asteroid's core.
Potentially, yes. How it's distributed could give us insights into Dimorphos' interior we just couldn't get otherwise. It's kind of amazing, really, that smashing something can actually teach us so much about it.
So even a deliberate smash-up becomes a scientific experiment. Very cool. Who are the key people behind this? You mentioned Alexandra Sokolowska.
Yes, Alexandra Sokolowska. She was at Brown University for a lot of this work, and now she's a UKRI fellow. That's UK Research and Innovation at Imperial College London.
Okay.
And also Ingrid Dalbar, a planetary scientist at Brown University. And we should definitely mention Gareth Collins again, professor at Imperial, who co-developed those crucial simulation tools.
Right, the simulation expert.
Yeah.
And if people listening want to, read the actual study.
They can. The findings were published in the Journal of Geophysical Research, Planets. That was May 13th, 2025. And it's open access, which is great.
Open access, perfect. Anyone can read it.
Yeah.
What's the DOI, the identifier?
Yes. The DOI is 10.1029-2024-JE008561.
Got it. And funding. This kind of work usually needs support.
It certainly does. This research got vital support from NASA, the UK Space Agency, and also the Swiss National Science Foundation. It really shows that international collaboration is key in planetary science.
Definitely. So let's wrap this up. The big takeaway is we've found a new, maybe simpler way to get clues about what's under the surface on other worlds.
Yeah.
Just by looking at the cosmic shrapnel patterns from impacts. It's like these collisions are doing surveys for us accidentally. We just have to learn how to read the mess they leave behind.
That sums it up pretty well. It adds this powerful new dimension to exploring planetary geology, maybe spotting hidden water or interesting structures on Mars and, well, beyond, all potentially from orbit.
It really is fascinating how something so destructive, a meteor impact, can become a tool for discovery. It paints a picture of hidden layers just from the fallout.
Yeah.
Makes you wonder, what other chaotic events out there might hold secrets if we just, figure out the right way to look at them?